So today we're going to have two, maybe three, but probably two independent lectures. The first is on subgradient descent. So subgradient descent, we finally are able to fearlessly attack problems that are not differentiable and use a gradient descent-like method to approach them directly. Whereas for the lasso regularization and for the support vector machine objective function, both of those were not differentiable, and we went through all types of manipulations to turn them into an equivalent but differentiable problem. Now we're going to develop some techniques that we can directly use a gradient method, subgradient method it will be called, on these objective functions. But on the path to get there, we're going to develop some more intuition on convex functions and some more terminology and general, some basic math principles related that I think will help us understand some topics more generally and will help later on in the course as well. All right. So to get into this, we're going to need a little bit more terminology. And it'll also give a little review of some of this convex optimization. So convexity at sublevel sets. So review, a set is convex if we connect any two lines with a line segment, and it stays in the set. The convex function, remember, are things that are bowl-shaped, kind of opening upwards. And if you take a graph of such a function and you connect any 2 points on the graph with the line segment lies completely above the graph of the function. So this is convex, this is not convex. OK. So this was the standard form for a convex optimization problem that we talked about last week. And remember that we have an objective function f0, we assume is convex. And we're minimizing that subject to these inequality constraints that fi of x, some function of x, is less than or equal to 0. And where we assume that each of the fi's are also convex. Each is also convex. All right? So a few questions to motivate this upcoming discussion. So less than or equal to 0. Was that arbitrary? Was this just, it's a standard form, so we have to define some standard, and so we're going to just, to be consistent, define the form of the constraint to be less than or equal to 0. But could we have also said greater than or equal to 0 and define that to be the standard?
It has to be, no, it has to be less than or equal to 0 in the sense it will be inside a convex set. If it's greater than 0, we're looking at outside that set.
Great. So what you're saying is that less than or equal to 0 is not optional. If we're greater than or equal to 0, the constraint set would not be convex. That's exactly right, and that's what we're going to work out in a few slides. Right? So less than or equal to 0 is not a coincidence. So let's make some definitions that are relevant here. So let's have a function f from Rd to R, and we'll define a level set, which we've talked about a lot, but I've never actually written a definition of a level set or a contour line. So a level set is a contour line, and we say that the level set or contour line for the value c is the set of all input points x for which the function attains the value c. Right? A sublevel set is similar. It's the set of all input points x for which the function is at most c. Right? Two simple definitions. And now we have a theorem, which is that if a function is convex, all the sublevel sets are convex. Let's look at a picture. And it's very easy to prove straight from the definitions of convexity and sublevel sets. So here's a convex function. This is a graph of a convex function. Nice bowl. Just so that we're totally clear, I'd like to review. What's the domain of this function?
R3.
The domain is the input, and it's R2. Yeah, it's the input. It's like the floor is the domain. That's the input. Now, this graph, what space does it live in? The graph lives in R3, right? Because when we talk about the graph of a function, like the plot of a function, the input is usually, we need dimensions for the input, but we also need an extra dimension for the value of the function. So if the input domain is Rd, the graph of the function is Rd plus 1. So the input domain is R2, and the function is a third dimension. All right. OK. So what's a sublevel set of this function? It's visually, you could take any value of the function that's a level in the third dimension, right? And we take a slice through the level set. And then all the values of x that have this function value or lower, so that would be this region of x, that's the sublevel set. And it's easiest to draw on a contour plot. So here's a contour plot. A contour plot is, of course, all of the level sets. This innermost circle is the level set for the function f of x equal to -1. So this is a contour plot for f of x. This circle is the level set or contour for f of x equal to -1. And the green is the sublevel set. It's all the points where f of x is less than or equal to -1. All right. Now, it's a convex function. And so the theorem, which is very simple to show, tells us that this sublevel set must be convex. Visually, it's convex. That's good. All right, and let's look at a non-convex function. So input domain of this guy, R2, all right? Is it convex or no? No. What does the contour plot look like? OK. So the green is the sublevel set f of x is less than or equal to -1. Is it convex? It's not. Each piece is convex, true. But the union of these three disks is the sublevel set f of x is less than or equal to 1. The function attains values less than or equal to 1 in all of these sets. And so if you take a point here and you take a point here and you connect them with the line, you're going to leave the sublevel set. So it's not convex. All right. So for convex functions, sublevel sets are convex. One other thing that's, again, very easy to show, and it's in our lab notes if you want to work it out in a few lines. The intersection of convex sets is convex. Right? There's two convex sets, and their intersection is visibly convex. It's easy to prove. And so now we can come back. Oh, and one other thing is that what about the other direction? So here's a circle. That's the level set fx equals, this should be -1. Is the level set convex? Just the circle piece? No way. You take 2 points on a circle. When you connect them, you leave the circle. So the circle is not convex. The circle and its interior, that's the sublevel set, the green piece. Is that convex? Yeah, that's convex. What about the superlevel set? That's everything where f of x is greater than 1. No, the purple piece, not convex. You connect two purple pieces, you're going to leave the purple set. All right. So if we think back to our convex optimization standard form, if f is convex, like it is for this example, then our inequality constraints are of the form f of x less than or equal to constant. And so those constraints correspond to feasible sets that are convex. If we had switched the direction of the inequality, f of x is greater than or equal to something, then that's a superlevel set, which in general for a convex function is not convex. That would be like this purple set. So back to the original form, what can we say about each constraint set x for each constraint set corresponding to function f sub I? It's convex. Why? It's a sublevel set for level 0 of fi. And we have a whole bunch of these constraints. So the intersection of the constraint of these constraints corresponding to each of the fi's, that's the intersection of a bunch of convex sets. And so that's also convex. All right. So what we've shown is that we're minimizing a function subject to x being inside a whole bunch of sublevel sets for all these different fi's. And it has to be in all of them, so that's like being in the intersection. And we know the intersection of convex sets is convex. So this is saying we're minimizing a convex function over a convex set. And in fact, that's another way to kind of generically express a convex optimization problem. Minimize f of x subject to x is in C, where C is some convex set. It's less easy to use, though, because how do you get a handle on what that, if you want to get a handle on that convex set, you're going to need to describe it in some way. And so this is much more functional. So what's coming next is we're going to look at functions that are convex and differentiable. This is the good piece. They have gradients. And we're going to talk about one particular property that we're going to leverage to generalize and develop this subgradient. So when we move beyond differentiable. So it all comes back to this first order approximation that we talked about a lot for differentiable functions and their gradients. And so the way to say is that we want to predict, we have a function, it's differentiable. We want to predict a function f at some location y, and we want to base it on the value of the function at some other location x and the gradient at this location x, right? And what we learned was that by looking at the gradient at one location, we can make a linear extrapolation on what we think the value of the function will be at some other location y. And so this would be an example. So here's a function. What's the input domain of this function graph here? Reals. Yeah, the input domain is reals. So there's a function mapping from reals to reals. So the graph of the function is in R2. Yeah. And we're trying to give predictions for values of the function f at any point y, say here, using information that we have about this function at this point x. So what information do we use at this point x? We use the value of the function f of x and the gradient of f at x, which in this case, what type of thing is the gradient of f at x? It's a? As an object, if you want to represent it in a computer or something.
Line.
No, gradient is, you think it's two numbers?
Something like the slope and
so what you're describing is some parameterization of this line. You need a slope and an intercept. But the gradient is actually just corresponding to the slope. So if this is the formula for the line, the two parameters you're speaking about are this piece, which is like the intercept, and this piece, which is like the slope. So in a function whose input domain is reals, what's the dimension of the gradient? Right. So if I can only move along this line, and the function takes some value just on this line, my gradient is a number, and it tells me it's either positive with the magnitude or negative with the magnitude. So for a function from reals to reals, the gradient is just a number, and it's just the slope of the graph of the function at that point or something. Okay. So yes, if we draw this kind of linear approximation to f as the line that it is, the slope of that line will be what goes right here. So in this case, written it as a gradient, but it would really just be like f prime of x, because it's just one dimensional. More generically, it would be a full vector gradient with dimension rd. Okay. All right, I think that's all we need to say here. So there's one other interesting property that we can already see from this picture, which turns out to be always the case when f is convex. So if f is, so here we're just saying f is differentiable. All right, we can always do this linear approximation if we have a gradient. But if f is convex also and differentiable, then this linear approximation is not just a linear approximation, it's also a lower bound. Right? So when we drew this tangent line, this linear approximation to f, it's not a coincidence that the line is strictly, except that is, or at least is always below or equal to the graph of the function. Right? this is actually, I don't want to oversell it, but it's a little bit profound in the following way, that we are getting global information about the function f just from information about the function at one point. So by looking at the gradient and the value of the function at just x, we've now found a lower bound that applies to this function everywhere. So that, of course, all derives from the fact that f is convex. So it turns out, although I don't state it in these slides, that for differentiable f, having such a global underestimator is necessary and sufficient for convexity. So that's a way to demonstrate you have convexity, interestingly. But here we're just using it as a consequence. If it's convex, we will have at any point a global underestimator made in this way. So what if we drop differentiable and asked for an arbitrary convex function, which doesn't have to be differentiable? What if we looked for linear functions or affine functions of this form, tangent to the graph, that are global underestimators? And then at any point that it's not differentiable, it's not going to be the gradient of f because there is no gradient, but it might be some other vector here, we'll call it g, for which f of x plus g transpose y minus x looks like this in the sense that it is a strict global underestimator of the function. And that's going to be our definition of a subgradient. OK, so that's coming up. But first, the global underestimator piece. Got a little ahead of myself. So I was saying it's a big deal that from just local information, you know something about the function everywhere. And one thing in particular that you know, that you can derive from this, is that a point that has zero gradient is a global minimizer. What happens when you plug in gradient 0 there? F of y is greater than or equal to f of x if, OK, so if we found a point x that has gradient 0, this second piece is 0. And so we're left with f of y is greater than or equal to f of x for all y. For all y. Yeah? So that's it. If f of y is greater than or equal to f of x for all y, for this particular x we found that happens to have gradient 0, that's proving that x is a global minimizer. There might be multiple global minimizers, but x is a global minimizer. So that's kind of demonstrating the power of convexity, that just from some local information about the function, you know what's happening, some piece of what's happening everywhere. All right. OK. So subgradients. So I've already spoken through what our definition is going to be. Let's write it down. So a vector g. Sorry, I switched from input domain to Rn, from Rd to Rm, but same thing. So for a vector g in the input space, if we can form a global underestimator of f using this linear expression in terms of g, then g is called a subgradient. If the thing is differentiable, this is definitely true if we plug in the gradient of f here. Right? So here's some pictures, and I want to walk through these very carefully. A lot of times they're mislabeled in books, and it gets very confusing. So the blue is the graph of our function. It's convex. It's not differentiable. Right? It's got these angles here and here. Right. The red lines, these are our global underestimators that we're talking about. They're our linear global underestimators. And what's interesting is that for a non-differentiable function, there's potentially more than one at a non-differentiable point. And here we've drawn 2. Right? OK. So the red line is a function of the form x maps to f of x0 plus g transpose x minus x0, right? Where g is the subgradient. So what space does g live in? Yeah? Okay, generically, Rn. Absolutely correct. In this picture, R. Yeah, this is a one-dimensional function, right? So in this picture, G is just a number, right? What is the number relating to these lines? How would you interpret this number in the context of this line? Yeah?
It's going to be bounded by the slope before that point, the slope afterwards, anywhere in between.
Oh, okay, so you've just characterized all possible values of G for which you get a global underestimator. Great, that's 2 slides ahead. That's great. I'm just asking, so for this particular line, G is a number. What is G characterizing about this line?
Slope.
Yeah, good. So G is the slope of this line. So the line is not a subgradient. The line is the underestimator corresponding to the subgradient through this expression for this linear. This is a line. Generically, it's going to be a hyperplane. What space does this hyperplane live in, generically?
The range of the R or
So if we graphed this hyperplane, just like we've graphed these red lines, what dimension does it live in? Rn plus 1, because the input space is Rn, and then we have one more dimension for the value. Just want to keep rehearsing it because I think it does get a bit confusing. Any questions on this? So yes, so visibly, yes, you can look for all the kind of the range of slopes for which you would get a underestimator as you were doing. And indeed, that range of slopes corresponds to the set of possible subgradients. So we say a function f is subdifferentiable at x if there's at least one subgradient at x. And the set of all subgradients is called the subdifferential. That's written this way. So when you suggested it's all kind of, it's this whole interval of possible slopes, that interval is called the subdifferential. Any individual subgradient, a subgradient. Okay. So here's a comforting fact. If f is convex and differentiable, then the subgradient is exactly, the subdifferential is exactly the gradient. Right? There's no extra g's that would give different global lower bounds other than the one corresponding to the gradient of the function. Another thing, so at any point there can be 0, 1, or infinitely many subgradients. So if it's differentiable, there's 1. Let me just give you the next bullet. If the subdifferential is the empty set, so in other words, it has no subgradients at a point, then f is not convex. In other words, any convex function has at least one subgradient everywhere. Right? So at any point x, there can be 0 subgradients if the function is not convex, 1 if it's differentiable at that point, or infinitely many if it's not differentiable, because as you intuitively saw, if you have kind of two different global lower bounds, you can interpolate all of the lower bounds between them. And although I don't write it on the slide, the subdifferential, it's a set of vectors. It's convex. And so you can take any 2 subgradients and join them with the segment between them, and every point along that segment is also a subgradient. So that gives you infinitely many subgradients. All right, so this is our definition of subgradient again. It gives us our global lower bound. And by the exact same argument, we find that if 0 is a subgradient, so it's an element of the subdifferential, there could be multiple subgradients at a particular point x. But if 0 is one of the subgradients, then by the exact same argument we gave for the differentiable case, x is the global minimizer of f. So just as in gradient descent, we're looking for something that has a gradient of 0 for non-differentiable functions, it's sufficient to find a point that has a subgradient of 0. All right, let's work an example. Absolute value of x. So here's the graph of the function on the left. What slopes do we need here to get a global underestimator?
-1.
-1. This is also the gradient here, the slope here. And here, 1. And here?
-1.
Yeah, anything with slope between -1 and 1 will give you a nice lower bound. So the subdifferential at x is 0 is the set of all numbers between -1 and 1, because here, our domain being reals, the subgradients are just numbers. So here's a plot of the subdifferential. It's not a function. It's -1, and then here it's multi-valued from -1 to 1, and then 1 to the right. Here's another function, a little more complicated. Input domain, R2. Absolute value of x1, the first coordinate, plus 2 absolute value of x2. Here's a 3D plot of it. We're looking for subgradients, or the subdifferential, at 3. Turns out later this is 3, 0. Right? So it's on the x1 axis. The x2 coordinate is 0. x1 coordinate is 3. So we want to find the gradient of this function, a subgradient at x1 plus 2x2. So let's kind of follow our nose here and see what we can come up with. So I'm looking for a subgradient, the subgradient of f, at the point 3, 0, I believe, is what we're looking at here. All right. So how about the first piece? If we were doing like a partial derivative with respect to this x1 at x1 equals 3, what's that going to be? Yeah, so the absolute value of x1 piece as a function of x1, everything else held fixed. Looks like this, to 0. So over at 3, the derivative is 1. So the first component of the subgradient is always going to be 1, because it's just differentiable with respect to x1 at x1 is 3. So that's 3. But then this other piece, all right, now we're going to have trouble, because we're looking for the subdifferential at 0. x2 is 0. And that's a non-differentiable point of the absolute value. So, but we already talked about what the subdifferential of absolute value of x2 would be with respect to x2. So what would the subdifferential be for the x2 piece here? If you believe that all the algebra that happens with derivatives also happens with subdifferentials, which they do. So, yeah, so if the derivative at 0, the subdifferential at 0 of the absolute value, remember, is from the slope of -1 to 1, so it's anything in the range -1 to 1, then multiplied by 2, that just gives us this range for x2. So any vector, this is informal, any vector of the form 3, let's call it G2, such that G2 is in -2, 2. That is the subdifferential of f at 3, 0. All right, fine. So suppose I took a G in this set, right? So where does this G live? It's a vector. Lives in
G2 or G?
All right, take G for some G in the subdifferential of f at 3, 0. If I write G is in R something, it's in R2, right? Right. The gradients and subgradients are in the input domain of the function. So this is the graph of the function. The domain is kind of these axes, x1 and x2. So that a subgradient will point somewhere, points in a direction of the input space. All right. All right, so suppose we take a g in this subgradient. So for example, g equals, give me a subgradient.
So it should be 1 versus 3.
Oh, did I make a mistake?
Yes, so it should be 1.
Thank you. Great. Okay, thank you. Okay, we're good now? Great. All right, so give me one possible subgradient for this function at that point. This defines a set of all of them. 1, 0 is a nice simple one. All right, so given a specific subgradient, we can construct a global underestimator. Every subgradient gives us a global underestimator of the graph of the function. So here's one. And do I write it on the screen? Okay. So the global underestimator is this linear function. I write h for hyperplane because the graph of it is a hyperplane. So f of 3, 0, the point we're differentiating at. G is any of our subgradients, so we've chosen 1, 0. This expression gives us the global underestimator of our function f. So we can plot that. So here it's hard to parse this picture sometimes. So this is a hyperplane, and it's resting up against this edge. Right? So this hyperplane is kind of on the bottom of the graph of this function, and it's resting up against the edge. And you could see that you could kind of rotate it around that edge, and at all those places, it's still a global underestimator for the function. Every one of those rotations corresponds to a different g, a different subgradient.
So it's global estimator for a given g, right?
It's a global underestimator for at any location x, you get a set of subgradients. You get a subdifferential, which is a set of subgradients, a set of vectors, g pointing in some direction in the input space. For every one of those g's, at every location, I wrote v here, at any location, for any v, for any subgradient there, we get a global underestimator. So at every point, we may get multiple global underestimators, or just one if it's differentiable. And then if we move to another point, we'll get a different set of global underestimators, either one if it's differentiable or infinitely many otherwise. All right, so sometimes this is easier to look at in the contour plot. So if we did a contour plot of this function, what space are we going to be looking in? R2, because contour plots live in the space of the input dimension, right? So remember, every contour here is a set of input values that give the same function evaluation value. So here, this blue contour is the set of input space giving for which f of x is equal to f of v for this one point v. Right? And then at this point, kind of corner point here, which is not a differentiable. This is the same function, by the way, just the contour plot of it. So it's not differentiable here, but we have a subdifferential. And these green arrows are a large selection of subgradients plotted on this contour plot at v. All right. So, and let's just make sure that you believe that that is a plot of this. So every green arrow should be 1 comma g2 for g2 negative 2, 2. So you see that if g2 is 0, this length would be 1. So that's the x1 piece. And then this would range from negative 2 to 2. Right? So these are a whole bunch of subgradients drawn based on the calculation we did over here. So one thing that you'll note is that if you look at the extreme subgradients here and here, it looks a whole lot like they are orthogonal to the contour line here. Right? Okay, not a coincidence. Not a coincidence. And understanding that helps with interpreting these sorts of plots. So let's dig into that a little bit more. So, all right, seems like one more review here. So for a function f from Rd to R, the graph of the function lives in what space?
RDP.
Yeah, RD plus 1, good. The gradient and subgradient of f live in input space, RD, good. The contours and level sets and sublevel sets are in RD, great. All right, so here's a theorem. Function f is continuously differentiable and at a point has a gradient that's not 0. Then, so the gradient has some length we can look at. Then the gradient vector at x0 is normal, so orthogonal, to the level set of all input values x that have the same value as x0. So we pick a point x0. We find the level set that contains x0. The gradient of f at x0 is orthogonal to that level set. Let's look at a picture. Maybe I'll draw a picture. Do I have a picture? Yeah, here's a picture. So this does not assume convexity. So here's going back to our example of a non-convex function. This is a contour plot. So here's a contour. It continues over here and over here. And at this point, the gradient vector is orthogonal to the contour. It's perpendicular to the tangent at that point. Right? So this is the picture illustrating the claim. This is for a differentiable function. Things are a little bit more complicated with subgradients, but we will work it out. So suppose we have this is a contour plot of a nice differentiable function, but let's go back to our contour plot. It's not differentiable, right? All right, and let's suppose we're looking at the level set for this point, x0. And I have this claim here. So the hyperplane, okay, so consider f has a subgradient g at a point x0. So this is x0, and let's draw a subgradient at x0. So this is a vector in the same space. And I'll write it as g. All right. And if this thing were differentiable, if we're at a differentiable part, then we know g is orthogonal to this contour line. But what's happening here where it's not differentiable? And this is the claim that the hyperplane h orthogonal to g at x0. So let's draw that. So here's our hyperplane h orthogonal to g at x0. Right? This is h. The claim is that it supports the level set. So the level set is this, the set of all x's that have the same function value as f of x0. And what does support mean? A hyperplane supports a set if it intersects the set and the entire set lives on one side of the plane. So this whole contour line lies on h or to one side of h. It doesn't cross h. So that is a supporting hyperplane. All right? So what we could show is that the supporting hyperplane corresponding to any subgradient, or rather, the hyperplane corresponding to any subgradient g is a supporting hyperplane for the level set. All right. So the proof is actually straightforward from this basic property of subgradients. Right? So if g is a subgradient, then we know that this linear expression is a global underestimator of fy. Great. For any y. Definition of subgradient. So now we're going to kind of do a proof by contradiction. So suppose we have some y, part of this level set, that lives over here, y. So this is y is strictly on the side of h that g points into. Right? So g points over this way, and let's suppose we have a y over here. And the claim is that this won't work. The claim is that if there is a y on this side of h, then it can't possibly be in this level set. See why? So the key reason is that so we're taking this inner product between g and y minus x. So let me change that x0 to x. Or I should have written x0 here is what's really going on. So y minus x is this vector. Right. And now we're taking an inner product between g and y minus x. So what's special about y being on this side versus on this side of h, as far as the inner product is concerned? Yeah, exactly. So if y is on this side of h, the inner product is positive. If y is strictly on this side, it's positive. If it's strictly on this side, it's negative. OK. Well, so if y is on this side, then this piece, if it's strictly on this side, then this piece is strictly less than 0, which means f of x plus something less than this. That means f of y is strictly larger than f of x. Let me write that out. Is that clear? F of y greater than or equal to f of x plus blah, which is something that's greater than 0. Which means so we're starting with f of x. We're adding something strictly greater than 0. We're going to end up with something that's strictly bigger than f of x. All right? So if we assumed y is over here, then f of y is strictly bigger than f of x. But if f of y is strictly bigger than f of x, then y cannot live on the same contour as x, because the contour has things that all have the same function value. So that means that no piece of the level set can be on this side of h. All right. So all elements of the level set S have to be on the negative g side of h, so pointing away from the direction g points into. So the reason we went through all this is to highlight what's one confusing aspect of subgradients, which is that they're not descent directions. So here's a picture. Again, the same function, the absolute value of x1 plus 2 absolute value of x2. And it's a contour plot. And we've chosen a g. And here's the hyperplane h. And what we've showed in this derivation here is that if we step towards a y anywhere on this side of the plane, the function value increases. That was because it increases, we know that it can't be part of the level set. But in particular, we found that it increases. So if we were looking to maximize our function, then a subgradient direction points in a direction that increases the function of the value. It's an ascent direction. The issue is, if you look in the negative g direction, in this plot in particular, it's not an ascent direction. Can you see why? Because the negative g increasing is going from an inner contour towards an outer contour. And so this direction is leaving this inner contour and going towards the outer contour. So the negative g direction is an increasing direction in this plot. Ah. All right. So not a descent direction. Subgradient is not necessarily a descent direction. The gradient is an direction of increase, but that is not of interest to us. We want to minimize functions. All right. OK. So to summarize, we're saying that take the hyperplane, points on this side have larger f values than f of x0. We have no idea what's happening on the other side. It could be both. And so it's not a descent direction. All right. But we can still say something. So let's go for it. Subgradient descent. What does the algorithm look like? Suppose f is convex. We're starting at some point x0. Repeat the following. Find a subgradient. Choose a subgradient direction. Step with step size t in a negative subgradient direction. Repeat. That is subgradient descent. We need some way to figure out what step size to use. And that's the algorithm. So the only question is, does it work? So it turns out the proof is really, really short. It fits on the rest of this slide, I think. Maybe I need a new slide. One more slide. The statement fits on one and the proof on another. So pretty easy to understand. So f is convex. What we're going to show here is that wherever we start, so I'm at x0, that's my starting point. I choose the subgradient direction, g, and I'm going to take some step that's a multiple of g, negative g. So that'll bring me here. And that's called the original point x0 and the new point x. Right? And what I want to show is that if there's some minimizer over there, wherever it could be, I'm writing it as z here. If z is some minimizer, some third point, when I move from x0 to x by stepping with a multiple of the negative subgradient, I'm getting closer to the minimizer z. What we're going to prove is that we can have any z. It doesn't have to be a minimizer. We're only assuming that the value of f at z is less than what we're starting. So this theorem also says that for any point where the function has a lower value than where we are now, we're getting closer to it. Right? So yeah. So I guess what that means is that the minimizer must be on the negative side of the hyperplane corresponding to any subgradient. Okay. So we'll literally show the distance to z, which could be the minimizer. It's something less than where we are now. From x, which is where we end up, is shorter than where we started. All right, that's what we're going for. Any questions? All right, this gives us the justification for using this crazy subgradient that we've been talking about. All right, so there's not much we can do, and so we're just going to do what we know, which is the definition of subgradient. It's all going to come down to that. So this is the distance between where we end up after a step and something smaller, the minimizer, say. Expand out the definition of where we step to, x0 minus tg, fine. This is the inner product of a vector with itself. We can open that up. This is the distance from where we start to where the minimizer is, and then we have this other piece. Right? The step size only shows up in these second pieces. And do you see where we can apply the one thing we know about subgradients? So this piece, G transpose x0 minus z. Remember our definition of subgradient? Let's write that down so it's very clear. So f of where we're ending up, x0 minus. So let's suppose we're going towards z. I think this is right. Is greater than or equal to f of x0 plus g transpose z minus x0, right? Okay. So we switch the direction. So we need this could be, let's bring the f of x0 over here. So we have f of z minus f of x0 greater than or equal to g transpose z minus x0. All right. Let's switch the sign. So that's f of x0 minus f of z is less than or equal to g transpose. Instead of switching the sign of this, we'll switch the order to make it look like that. x0 minus z. All right. So can we apply this to get the claim there? All right. So g transpose x0 minus z, we replace it with something smaller. We're subtracting something smaller, so the value gets larger. So that's why this is greater than or equal to this. All right. So this inequality is simply from the definition of subgradient. All right. So we have one more thing we can work with, which is the step size t. What kind of thing is this as a function of t? It's quadratic. So we know how to minimize quadratics in closed form. So we could, for instance, take this minimum of the function at this particular value of t. So it turns out, sorry, I jumped ahead. I was going for the best possible step. But all we need is, what do you want to happen? We want this to be smaller than this, which means this whole expression must be negative. Right? So we need this whole thing to be less than 0 for this to be interesting, because we want to get closer. We want the distance to be less than this. So we're looking for this to be less than 0. We could find the zeros of that function, 0 in here, and it's convex, it's facing up. So we know this thing will be negative whenever t is between these two values, the two zeros of the convex function. That's what's stated here. So if your step size is anything in this range, we're guaranteed to get closer to the minimizer. Wow. That's the theorem. Now we actually know the actual minimizer of this function. It's the point right in the middle of these two zeros, right, by symmetry. So in some sense, the optimal step size would be, at least with this reasoning, would be exactly between these two. But can we actually use that in practice? Because we don't know z, right? So to figure out this endpoint, we're going to have, z is the minimizer, or something smaller. And we have to know it to figure out the right step size. We don't know it. So we can at least say if we take a small enough step size t, close enough to 0, it'll decrease, all right, even though we don't know f of z. All right, so that's nice. This tells us we're getting closer. We still kind of want a little bit more, which is a theorem which tells us that we'll get there eventually. So there's two theorems, two convergence theorems. I don't think we need to dwell on the details. One is for a fixed step size, and one is for a step size decreasing with like Robbins-Monroe style conditions like we talked about in the second lecture. It's like 1 over n or something like that. Unfortunately, there's no good characterization for a stopping condition here. So remember, with gradient descent, we can look at the norm of the gradient. And when that's really small, we're like, OK, we're basically done making progress. We're not really decreasing the function much. But subgradient, why is that not going to work at all?
Because there's not one single subgradient, right?
Yeah, so there's multiple subgradients, right? But not every subgradient decreases your function at all, right? Sometimes you have, so a subgradient may not even be a direction of descent. So we can't just be looking for when our function stops decreasing, because the increase may be part of the path. So I don't actually know of any kind of good rule for saying a stopping condition for subgradient descent. I think in practice you basically do what you do anyway, which is look at when your performance, say on validation set, stops improving or something like this, when you run out of patience for it.